Alright class, this is Ms. Riggins coming back with a new set of videos, and we are in, I believe, Unit 12, and it's on a different type of functions that we have not been talking about. And if you remember at the last part of the fall semester, we started talking about the different types of functions that we've been exposed to in your high school math career, and we talked about linear, absolute value, and quadratic. And then beginning of the semester, we talked about cubic and polynomial functions, and weakened it off with rational functions. And today we're going to talk about a different type of functions that's also on the list on page 109, which are exponential functions and later on logarithmic functions. And so that's what we're going to be focusing most of our unit on, and it's a short unit. So if we take a look at an exponential function is very similar to a polynomial function. A polynomial function, if you remember, has a power of y, f of x is equal to x to the third. And that's also the example of a cubic function. So this could actually is the parent function of a cubic function, but here a polynomial function has x as the base of the power and a number like 4, 5, or 6, or any whole positive number as its power. Well, in a exponential function, it's a little bit different. An exponential function has, instead of x to the third, it would have a f of x is equal to 3 to the x, or 0.3 to the x, or 2.3 to the x, where the base is a constant number, and it's a positive number between greater than 0, and x is a power. So as the x value changes, the number of times I'm multiplying the base by itself changes. So the graph of an exponential function looks a little bit different. The graph of an exponential function looks kind of like this. And as you can see, two things to note about it. One is the domain and the range, and as you can, actually there are three things to note about. One is the domain and the range. The domain is all real numbers. There's no holes or gaps or breaks, and there's no vertical asymptote. So it's actually can go on forever in this direction and going to go on forever in that direction. But the domain is not, but the range is not all real numbers. In fact, it's a subset of real numbers, and in this case, it's all positive real numbers. So the thing to note about this function is that the domain is all real numbers, but the range is a subset of that, and it's either all positive numbers and real numbers, or vice versa, depending on the transformations, which we're going to talk about later. And as you can see here, that there is this horizontal line that the graph will not cross. And for this function, that horizontal line is the point, is a horizontal asymptote that has the equation of y equals 0. So that's why in an exponential function, you do have a subset of the real numbers as the range, because it cannot go below the horizontal asymptote, which in this case is at y equals 0. So that's the second thing to note, which is the horizontal asymptote. It always has at least one horizontal asymptote. And then the third thing to note is the Y-intercept. And we're going to take a look at here. As you can see, every exponential function does cross the y-axis, but not every exponential function crosses the x-axis. In this case, it's impossible for this function to cross the x-axis, because the x-axis is also the horizontal asymptote. So we're going to take a look using Desmos.com to see the different type of exponential functions and how they look. So here we have a graph of an exponential function with a base of 2.3, and as you can see here, it still has a horizontal asymptote at y equals 0, i.e. the x-axis, and it also has a range of all positive numbers and a domain of all real numbers. And as you can see, it passes through the point 0, 1. So even if I change the base value from 2.3 to, let's say, 44, as you can see here, it still crosses through the point 0, 1. It still has a horizontal asymptote, and it still has a restricted, it still has domain of all real numbers and the range of all positive numbers. Let's see what happens if I change from a smaller number to a bigger number. What happens if I change to a smaller number. Instead of 2.3, let's change to a number that's less than 1. Let's say 0.5. Well, as you can see, the direction of the graph has changed. It's no longer increasing, but now the graph is decreasing, but it still has a horizontal asymptote at y equals 0. It still has a domain of all real numbers, and it still has a range of only positive numbers. And so no matter how I change the value of the base value, as long as it's a positive number, it's going to still have those three characteristics. No matter if it's a decimal, even if it's a fraction, as long as that base value, oops, let me erase this to the x value, as long as that base value is a number greater than 0, you're going to have those three same properties, as you can see. It still is going to have a domain of all real numbers. It's still going to have a range of positive numbers. It's still going to have a horizontal asymptote at y equals 0, and it's still going to go past the point 0, 1. So now let's take a look at what happens when we do some transformations to this basic function value. And I'm going to change the base to 2, a nice lovely whole number, so we don't have an issue. If you recall, on page 111 last semester, we talked about the different types of functional transformations, and we carry that over into this semester. And we said for any function f, if I add a k, positive number k, to the function value, I'm going to get a vertical shift. And if I add a positive number k to the x value, I'm going to get a horizontal shift. And then we talked about the different reflections across the x-axis and the y-axis. And then we talked about the different type of compressions. By multiplying a number times the function, I will get a vertical compression, and multiplying a number times the input, I will get a horizontal compression. So even though the function is not specific, we still have these same situations. And that's going to occur even with an exponential function. So right now we're going to talk about the 3 different sets of transformations that can occur with exponential transformation. So let's see how the graph changes if we change to a different function. Instead of 2 to the x, oops, I do 2 to the x plus 3. And as you can see, the graph did translate up 3 units. How do I know it's up 3 units? Well, if you remember in the original graph, it crossed the y-axis at 0, 1. Let's see, where does this new graph cross the x-axis at? It crosses the y-axis, not x-axis, sorry, y-axis at 0, 4, which means it did a vertical shift, from 0, 1 to 0, 4. Let's see what happens if I change it from a vertical shift up of 3 units to, let's see, if I change it to a vertical shift of 5 units down. So subtracting 5, so instead of our starting value or our y-intercept at 0, 1, we have it now at 0, negative 5. Oops. Sorry, not 0, negative 5, 0, negative 6, because it was originally at 0, 1. Now it's going to be at 0, negative 4. Sorry, I'm still on vacation. And that's because I shifted it from 0, 1 to down 5 spaces to 0, negative 4. Now let's see what happens if, instead of adding or subtracting a number to the function value, I'm going to add or subtract to the input value. So instead of 2 to the x plus 3 or 2 to the x minus 5, I'm going to do 2 to the x plus 3. In other words, the plus 3 is in the power function. Oops. All right. So now it's going to be 2 to the x plus 3, and look and see what happens. Now we have here, it looks like the graph shifted to which direction? To the left. And how many units do you think it shifted to the left? It shifted 3 units to the left. And how do I know it shifted 3 units to the left? Well, let's take a look. Our starting value was at 0, 1. So what seemed to happen? Well, as you can see here, the y-intercept is no longer at 0, 1. It's all the way up here at 0, 8. But what I want you to take a look at is here was my original function point, starting point is 0, 1. And let's see what happens if I move this point over 3 units to the left. So now that point would be negative 3, 1. And look, as you can see, this starting point moves to the left 3 units. If I change this from an x plus 3 to an x minus 5, let's look to see where this point comes. The starting point moved from 0, 1 to, looks like over here, to be at 5, 1. And as you can see, that's where the point moved. So a way to identify exactly how many units in a transformation move to the left or to the right is by using the starting value. Okay, there's also some other transformations that we're going to go by really quickly just so you can see, which is what if I want to reflect it over the x-axis. So instead of 2 to the x, I'm going to do negative 2 to the x. And look, it reflected it across the x-axis. If I want to reflect it across the y-axis, instead of making the base a negative, I'm going to make the power a negative. And as you can see, it reflected across the y-axis. If I want to do a horizontal compression, or a vertical compression, well, let's see. I'm going to multiply my exponential function times a number, and that if that number is a positive number greater than 1, it's going to make it get closer to the y-axis, i.e. narrower, and if it's less than 1, like 0.5, it's going to make it wider than the parent function, or wider than farther away from the y-axis. And now we're going to take a look in doing that. What happens if I multiply the power by a number? If the number is bigger than 1, as you can see, it kind of makes it go narrower to the x-axis, and if that number is smaller than 1, let's see, 0.4, it makes it wider. It's hard to see a vertical and a horizontal compression, the difference between the two, because of the way this graph is. So they basically look the same because the graph is always increasing or always decreasing, so you can't really see the difference between a horizontal compression and a vertical compression. Okay, that's it. Sorry this video was long. I promise you the next one won't be as long. All right, have a good day.